Okay, let's have the shear and moment diagram construction as well as sketching of elastic curve for this frame. For the frame loaded as shown below, construct the shear and moment diagrams, also sketch the elastic curve. So this is the given figure. So first, let's compute for the reaction components. So those are the indicated directions. So summation of moment about A equals 0, counterclockwise positive. So we have RD times 17 equals 26 times 12 times 6 plus 12.5 times 12 times 6 plus 5, so 11. Therefore, R sub D is 207.176 kilonewtons. Likewise, summation moment about D equals 0, clockwise positive. So we have 26 times 12 times 6 plus or equals AY times 17 plus 12.5 times 12 times 6. So solving for AY is 57.176 kilonewtons. Let's now transmit the load over the length AB, or summation versus X first, so solve for AX. So 26 times 12 equals AX. So AX is 312 kilonewtons. Then this is member AB. The load is the load is over the vertical projection 26 times 12, but over the length AB. The length of AB is square root of 5 square plus 12 square, which is 13. So the load over AB would be 26 times 12 divided by the length of AB, which is 13. So it is now distributed over AB, and its equivalent is 26 times 12, which is 312, divided by the length of AB, 13. So that would be 24 kilonewton per meter. Then let's resolve this load into normal or perpendicular to AB and tangential load. So this is theta 1, and opposite to theta 1 is 12, adjacent is 5, hypotenuse is 13. So that W normal 1, so this is also theta 1, W normal 1, this is W tangential 1. W normal 1 is 24 times sine of theta 1, which is 12 over 13. So that would be equal to 22.154 kilonewton per meter, while W tangential 1 is 24 times cosine of theta 1, which is 5 over 13. So in decimal, 9.231 kilonewton per meter. So let's now put the values here, 22.154 kilonewton per meter, then up 9.231 kilonewton per meter. Then let's have AX and AY. Then this component reaction should be resolved into shear or force perpendicular to AB and parallel to AB. So I'll call that shear as VA and normal to A. So from the figure, VA is 312 times sine of theta 1, or 312 times 12 over 13. It's in that direction, while 57.176 is in the opposite direction. So minus 57.176 times cosine of theta 1, which is 5 over 13. So VA is 312 times 12 over 13 minus 57.176 times 5 over 13. So VA is equal to 266.01 kilonewtons. While NA is, because 312 is in the direction of NA, 312 times cosine of theta 1, 5 over 13, and 57.176 is also in the direction of NA, so it is plus 57.176 sine of theta 1, which is 12 over 13. So 312 times 5 over 13 plus 57.176 times 12 over 13. So NA is 172.778 kilonewtons. Then let's call that NB, shear at B, and moment at B. So for portion BC, uh, over the horizontal projection 12.5 times 12, but over the length of BC, the length of BC is square root of 12 square plus 3.5 square. So it is equivalent to slope of 12 horizontal, 7 vertical, so hypotenuse 25. So this is 12.5 times 12 divided by, the length is square root of 12 square plus 3.5 square, so 12.5. So this intensity is 12.5 times 12 divided by the length of BC, which is 12.5, so 12 kilonewton per meter. Then we resolve it into W normal 2 and W tangential 2. So W normal 2 is 12 times cosine of this angle, which is 12, which is 24 over 25. So by the way, going back here, NB is equal to NA, 172.778 minus 9.231 times 13, the length of AB. So NB is 52.775 kilonewtons. While V sub B is VA minus 22.154 times 13, and MB is VA, which is 266.01 times 13 minus 22.154 times 13 times 6.5. So it's just like summation moment about B to solve for MB. And therefore MB is, in that sense, MB is 1586.117 kilonewton meter. Or another way of computing MB is based on these reactions here. So summation moment B equals 0. It is AX times 12 AX times 12, that's clockwise, minus AY, which is 57.176 times 5, minus 26 times 12 times 6. So it will give us the same answer, 1586.12 kilonewton meter. That's also 0.12 kilonewton meter. Then in this figure here, so this is theta 2. The slope is 7 vertical, 24 horizontal, 25 hypotenuse. So WN2 is 12 times 24 over 25, 11.52 kilonewton meter, while W tangential 2 is 12 times 7 over 25. So it is equal to 3.36 kilonewton per meter. So we now distribute the normal and the tangential load. So 11.52 kilonewton per meter, and this tangential load is 3.36 kilonewton per meter. And let's compute back vis-a-vis here from this figure. So it is equal to 22.154 going down minus 266.01. So vis-a-vis is 21.992, or summation forces in that direction equals 0. V sub B plus V sub A equals 22.154 times 13. So that's why V sub B is 22.154 times 13 minus VA, which is 266.01. Then here we have RD, which is 207.176 kilonewtons. Then let's resolve this into normal, shear and normal. So V sub C, we have N sub CB, then here we have NBC, then shear BC. So let's have it on the next slide because we ran out of space here. So let's continue. Let's use the joint B. This was the shear at B, 21.992. Then NB, which is 52.775, moment at B, and so that's just the positive. Call that shear BC and BC. Then This is the member BC, and this was the free body diagram in the preceding slides. So summation forces X equals 0, right toward positive. So we have VBC times 7 over 25 plus NBC minus NBC 24 over 25 plus 21.992 times 12 over 13 or sine theta 1 minus 52.775, this is to the left, times 7 times 5 over 13 rather, equals 0. So simplifying, 7 V share BC minus 24 in VC equals 0. Call that equation 1. Summation forces Y equals 0. So VBC times 24 over 25 plus NBC times 7 over 25, the vertical component of NBC, then equals 21.992 times 5 over 13 plus 52.775 times 12 over 13, the vertical component of this. Remember the slopes for this member here and for that member. So simplifying, 24 share BC plus 7 NBC equals 1429.346, equation 2. Solving these two equations simultaneously gives us share BC 54.887, this one or that one, and normal to BC is 16.009 kilonewtons. So shear at C is 207.176 times 24 over 25, 198.889, while NCB is 207.176 times 7 over 25, that component, so that would be 58.009 kilonewtons. So let's check if this member is in equilibrium. So NBC, which is 16.009 plus 3.36 times length of BC 12.5, then minus NCB, which is 58.009. That's almost 0, so that means it is balanced. Then for shear, V sub C, which is 198.889, then minus VBC, which is 54.887 minus 11.52 times 12.5 is also almost 0, so that checks. Let's check if moment at C is 0, which is expected 0 also. So MB, which is 1586.117, then minus VBC, which is 54.887 times 12.5 minus 11.52 times 12.5 times 6.25 moment arm, that's also almost 0, so that's okay. We have checked that member BC is in equilibrium. Now we are ready to sketch the shear diagram. So remember the shear at A from the previous slide. So it's begin with 0. So shear at A is 266.01. Then minus the loading, times the length of member, which is 13. So that would be negative 21.992, which is this. So it closes there. Then this distance is solved by similar triangles, or the direct way is 266.01, this shear here divided by the normal load in AB. Then it will give us a value of 12.007. Again, you can solve 12.007 by similar triangles. This is 13 meters total length, or 266.01 divided by W normal 1, and you'll get 12.007. Therefore, this distance is 0.993. 13 minus 12.007, so 0.993. Then this is shear BC, which is 54.887 negative, then minus 11.52 times 12.5, the length of BC. It will give us more or less 198, negative 198.889. So it's negative 198.887. And this is 198.889 for shear C. So that's closest there, almost 0. And that's it. because in this portion, the reaction is vertical, so there's no shear in this portion and there's no moment about that point. So that's the shear diagram. For the moment diagram, then we have this area here, 1/2 of 12.007 times 266.01 is area 1, and that's area 2, and this is area 3, trapezoid. So area 1 is 1/2 of 12.007 times 266.01 is 1596.991 kilonewton meter. Area 2 is negative 0.5 or 1/2 of 0.993 times 21.992. So this is 0.993, 13 minus 12.007. So negative 10.913. Area 3 is negative. It is area of trapezoid, 1/2 or 0.5, 54.887 plus 198.887 times length, 12.5. So area 3 is negative 1586.088 kilonewton meter. So let's now construct the moment diagram. The moment at A is 0 plus area 1, which is positive, decreasing. So it looks like that. 1596.991. Then minus area 2, 10.919. So that gives us moment at B, which was 1586.071. So the discrepancy, which is very small, is due to rounding off of this distance and the calculation of areas. So as a result, there's a little discrepancy, which is acceptable because that's very small. Then we begin with 1586.071 moment at B, or 1586.117. They should be equal, but I still stick to 1586.117, which was the moment at B. Then plus area 3, which is negative 1586.008. So that closes almost 0 there. So this is the moment diagram. And here, there's no moment diagram. There's no moment in this member here. So for the elastic curve, then this is positive moment. So it looks like that. This is also positive, concave up also. Then because this is ruler, so it will be moved to the right. So this is the elastic curve. Looks like that. And that's it. That's the expected elastic curve. So I hope that you were able to follow the solution. Sketching frames, especially if members are sloping, is quite a bit challenging, but if you just know how to transmit the loads over the member and compute the normal and the tangential components of the loads, as well as computation of shear and normal components, then the rest will be about statics, and you can check if it is in equilibrium. Then you can master sketching shear and moment diagrams for frames, as well as the sketching of the elastic curve. So thank you for your time.